So thank you all everybody for attending again the Answer Cohesa Seminar Series. It's our pleasure to have Masum Hossain, our co-PI from the University of Alberta, talking to us today. He's an expert on hardware, low-level hardware design, in particular circuits, and he's been, as he told us last time, he's been active in the area of mixed-signal circuits for specifically for machine learning. This is an area with a long history, but things have changed quite a bit, and we're looking forward to hearing what Masum has to say today. And again, just a reminder, on July 5th and 6th, we're going to have the annual general meeting, and where you're going to have the opportunity to see what everybody else is doing. And hopefully it's going to be a very productive 2 days for all of us. So thank you, Masum, for taking the time today, and please move ahead.
Okay, thanks for the introduction. So this is me as PI, but these are my students. I have currently 3 students working on it, and later on, as we present different part of the project, their status, I will be able to attach who is doing what and what is their update on that. And one of the students hopefully will be attending next month's meeting on 5th and 6th, and will be able to explain his work by himself a bit better, hopefully. So, okay. So what I wanted to talk about was the scope of link design for Cohesa, right? So we have been doing link design for a while, but those were for general purpose, right? We didn't want to just do another link design. We wanted to do something that is relevant to machine learning. So we'll define that scope, what is happening out there, how people are using these links, for example, NVIDIA and other people, and try to learn what specific they are doing about it to make it adaptable to this machine learning effort, right? And what it comes out is that we'll see in these links, they are providing the bandwidth. Obviously, it's understood by now, these links has to provide much wider bandwidth because we are processing a lot more information now, right? And at the same time, a lot of devices will be mobile. And even if they are connected to a power supply, we want to be energy efficient, right? And when we say energy efficiency, it's most like signaling efficiency, meaning if I have to send a stream of bits from one end to the other end, how efficiently, burning the least amount of power, I can do that, right? But while talk about it, there is one more thing, is that the information efficiency. What that means is that not every bit carries the same amount of information. Can we do something in the link design and that can accommodate that? So far, we never did it because the links were standalone and we are kind of isolated. But this project allows that opportunity to happen, that we can probably explore the information efficiency, right? And then comes the analog mixed signal computation part, where we traditionally do it digitally. But if we do it in some other ways, for example, phase or time, as the quantity, is there a power and resolution improvement possible or not? Then the last part is to combining these two together, right? So the hope here is to see some synergy, right? It's not just a standalone link with a standalone processor. If they're co-designed, there has to be something better coming out of it, right? So 1 + 1 should not be 2, it should be 2.5. Hopefully could be more than that, right? And along that line, a couple of the things in the Cohesa goal that we put is the quality of service, means the link should be able to adapt its energy according to the quality of the link that it provides, right? And then the computation memory and those things. So lastly, we'll say where we are now and where we are hoping to be, hopefully in a year or so. And this is the time also to get feedback, because other people are probably also doing things. If there is some overlap, we try to leverage it. If there is some complementary things, then we want to work together, right? So that's about it. So now if you look at what is out there today, like NVIDIA, they kind of advertised their NVLink. NVLink is basically their proprietary link that they use. And the way it sort of advertised is so much better than PCI and other links that allows this Tesla GPU to do really fantastic things, right? So now, if we think about it, where these links go to is actually inside this green line. So they have 4 GPU here and the other 4 on this side, and these links, these GPUs are connected through these green arrows, and those green arrows are basically showing the NV link, right? And any GPU can talk to any other GPU through those links. And then they also have the standard PCI links, and those goes from these green boxes to the PLX switch. So that is when they have to talk to outside world. And this is the NV links are really to talk inside from one processor to the other processor sort of way. So when they say there is a bit of a marketing advertised to it, these links are like 80 gigabyte per second, and compared to like PCIe, which is 16 gigabyte per second, they're saying we give you 5x the bandwidth, and then obviously much more CPU memory speed, and also 3x lower energy at the same time. So it seems like these guys are way smarter than the people who are designing PCI, because they're giving energy efficiency and performance improvement at the same time, right? Well, we know that that's not always the case. We know both sides are designing their links with the best guys available. So where is the catch? Where is this improvement coming from, right? So NVIDIA was not showing a whole lot of inside those links or how they are connected. But one thing that came out very clear from few other presentations, in a more informal way, but there are a few formal ways to see that the links that supports these NVLink and the links that are in PCIe, they are very different type of links. This one is much more lossy. It is a general purpose. It has to compensate 30-35 dB of loss, crosstalk, reflections, many other things. So the links that these guys use inside from one GPU to the other one, these are way more well behaved. So half of the engineering is making those links so much better. So frequency dependent loss, reflections, everything is so much better. And they leveraged all of that in the link design that got them the speed and the efficiency that they advertised. So one good example I could find that was like from AMD, they made the public demonstration of this link is that they actually put multiple cores like the GPUs on the same package, right? So this one is showing 4 cores of those. And these are the links that they have, right? So now the thing is that none of these lines or the small trace that they have needs to come outside the package, so they can and maintain very good signal integrity. The loss and everything would be much better. And that's one of the things Tesla is doing too, and other peoples are doing too, right? So this is why inside, like what they say these days is within the package bandwidth, that's 256 gigabyte per second. That's a huge bandwidth that they can accommodate. And if you want to see some of these channels, they look pretty like it's like a congested traffic. If you look at in any highway, that's how it looks like. So these are the 4 chips or the processors, you could say. And these are the high speed lines. The blue arrows are the high speed lines. So, and this is how they do the routing. So the package technology has improved enough that they can do this sort of things these days. And if you look at the response of these traces at the speed they're running is very, very small, 10 dB or less, right? So in a way, if for the machine learning and other things to happen, the sort of bandwidth they need, it kind of has to be pushed the limit from every front, right? The package technology has to be there and the circuit design has to work with it to give the sort of energy efficiency. Because if we look at the previous PCIe gen versions, their speed and energy efficiency will improve with innovative circuit design, but they will probably not reach at the same level, right? So, and that's kind of what we are trying to do for this project. And we are trying to take these channel responses, and I actually gathered a couple of those responses here. I'm just showing one, for example, and we studied how much the performance we can push given we leverage this level of improvement in other things. Now, one difficulty that I have while doing that is that we don't have access to such good packaging technology to this level. We have some through CMC. They do silicon interposer these days, and I'm asking them, let's see if we can have some of it available to us, or I have to look for an alternate way to do that. So now going back to this, what does a link look like? So I know most of the audience are not circuit centric, so I wanted to give a very brief background on this. So what these links do is that they basically take from the left side all the low speed data and they serialize it, right? And once serialized, they transmit it. And then this transmitted data comes over this channel. And then we may have to do a little bit of equalization and then read the data. So what it looks like is a functional view of it is like this. We have this whole bunch of zeros and ones, and we have obviously it's a synchronous system. So every rising edge is going to transmit one of those bits. And what it shows up on the other end is a voltage signal, which ideally it would be differential and separated by some amount V peak to peak. And that would represent the bit that we are transmitting, right? That's the whole point of these serial links, right? So it by itself, it's not too difficult, but what makes it difficult is that see the signal that I am sending here and the I or the separation that I'm showing here, that kind of does not always remain like this. And that's why it's very difficult to detect the bit on the other side. And that's where all the challenges, equalization comes into picture. But keeping it simple for the time being, the other thing that looks like is that, see, every bit is detectable by the voltage difference and this V peak to peak. So that in our world, we say signal to noise ratio, right? So wider they would be, more reliably we can detect them, but making them wider or this V peak to peak higher would also consume a lot of power. And that is the signaling power that everyone is trying to improve, right? So because at the end of the day, both sides are terminated with 50 ohm, and across a 50 ohm resistance, the only way to get a bigger swing is burning more current and more power. So it looks like a very fundamental limitation going close to Ohm's law, right? You have to get the voltage, you have to burn the current across the resistor. But we still try to play the tricks around it to make it more efficient. And as far as the link goes, we are trying to take advantage of the channels, like relatively better channels that we have access to, and keep the equalization complexity low enough so that we can hit very good efficiency, less than 1 picojoule per bit, right? That's the goal. So now why getting the signal swing is difficult? If it can be explained in a very simple way, right? So the simplest solution is to say that, well, I have to send this data bit D. So I'm going to basically drive some amount of current to that load resistance, right? By controlling these switches. So the way it works, you can imagine if I am sending D equals 0, so this switch would be completely off and this switch would be turned on. Means now this current is going to come from the right branch, right? But the way this current comes is half of the current is going to come from this resistor, the other half would be coming from the other end of the resistor, right? So this node voltage, as you can see, would be, if this is say VDD, for example, it would be VDD minus IR over 2. So this current would be half, because if my total current is I, not all of it is coming from this side, it's only half of it is coming from that side. So that reflects the voltage drop here. And on the other side, it would be pulled to VDD because there is no current being pulled, this switch is completely off, right? Now, if I flip this scenario and I turn on this switch and turn off this one, then what happens is that I/2 current that was coming from the bottom path, it now would be coming from the top path. So basically, you see the difference between the voltage level between D0 and D1, you can calculate it from here, it comes to IR, right? That's the received signal amplitude that I can translate to by burning I amount of current. And this R, for our case, and most of the high-speed case, these are all 50 ohm terminations, right? Because the channel has 50 ohm characteristic impedance. Now, if you look at it, how do we make it better, right? So one of the ways this is inefficient is because the current is only coming in one direction, right? It's either coming this way or not coming at all. For example, here it's just VDD, right? So if you want to make these things more efficient, you have to be able to push and pull the current. So the current has to be somewhat bipolar, right? So this is kind of what happens when you try to make it bipolar, right? You kind of envision that from the current will come from top and the current will leave from the bottom and vice versa, right? So this one is more like a bipolar driver, right? So the way it works is also simple, that one of the switches is going to be turned on. So the current path, if you can look at it, it will come down here. And it actually is, this is the other switch that would be turned on. That means the current will flow through this node, through the channel and circle back to the bottom node and leave it here, right? So in this case, the interesting thing is that this I is going to flow through these two resistors. So I'm going to see 2R instead of R like the previous case. So this way, just this difference gives me IR drop. And when I reverse it, I'm going to see the exact opposite. So the current in this time comes round through the right side and through the bottom transmission line and reverses its direction and to reach out on the other end, right? So if you look at it just by doing this simple reconfiguration of the switches, I can double my switch, the swing now. It's now 2IR instead of IR that we saw the last time, right? So now if we follow this thing, there is one thing still a bit inefficient about it. And that part is because, see, it's always I/2. It's I/2 because your receiver side has some sort of, the transmitter side has some sort of termination. That means as soon as any nodal equation means half of the current would be burnt on your transmitter side and only half of the current can go on the other side. So that makes it inefficient from power consumption point of view, because ideally I want all the current be gone through this transmission line and create the voltage difference on the other side, right? So how do we do that? A simple way to look at the Thevenin's equivalent, right? Is Thevenin's equivalent says that if you have a current source in parallel with a resistor, you can convert it into a voltage source with a series resistor, right? So this way, when you convert it, then all the current you can imagine are now going through to the other side, because this termination is now in series instead of parallel. So it is not going to take away half of your current every time, right? And for sure it does that way. And now if you turn on this switch and turn on this switch, then all the current would be going through this series termination and circle back. And the other way around, if this switch is turned on and this switch is turned on, then the current flow path would be from the right side through this guy and circle back, right? So this way now all the currents are going into the receiver side, giving me 2x further improvement. So I will total get 4x improvement compared to where I started. So this is kind of just a little bit of understanding how, to which extent we go to convert every milliamp of current to a bigger swing at the receiver, right? And this type of things are now understood and common. And even we built this type of transmitter. This one was built in 65 nanometer. They are very compact, power efficient. I did not include all the information for this, and it shows a fairly decent I for the given power consumption. It's pretty efficient. Now, the thing is that we have to do something different to push it above this limit, right? So now if you look at it, the way things have gone so far is that we take this current mode driver, we make it bipolar, we make it voltage mode, and every step gives me 2x improvement. But it kind of is hitting to a limit that there is very little room to extract more information out of it, right? So this is why we have to look at it, well, we have done nearly as much as we could from these transmitters, but what next? And that's where probably we can do it more information efficient way to get the next 2x improvement out of it, right? So the idea is sort of simple like this. We say that, well, the data bits do carry the information, but what happening, the change of data bits probably is more accurate description of the information. So we say that we will take this simple driver, but we will not directly drive them with the bits. We will drive them in an encoded manner. For example, these switches would be driven when I will have data and the previous data different, like 1 to 0 transition. So 1, 0 transitions are going to drive this switch X. 0 to 1 transitions are going to drive those switches. And then when there is no transition, I'm going to simply turn on this switch and the others would be off, right? So if you think of it in this way, means this switch would be turned on when I get consecutive 1s or consecutive 0s. So how does that changes the signaling picture, right? So let's start with a simple example of 0 to 1 transition. That means just like a regular voltage mode driver, right? You turn on this switch and this switch, so the current flow would be through the top path and circle back to the bottom, and I would get my IR voltage drop. And then the other way around, 1 to 0 transitions are also done in the exact same way like a voltage mode driver. So there is no difference here. We get my 4 IR voltage drop for the I amount of current. But the last mode is something that is different. So what is happening here, I disconnect all the switches, right? Both on top and bottom. So, and I turn on this switch. So it is basically self-terminated. These two resistors in series, they are shorted together. And on the other side, if they are shorted together, I basically have no current flowing through it. So it is showing V1 minus V2 is 0. So one might ask, like, what is the reason if there is no differential voltage, why we needed even to turn it on? Because there would be still some ringing that needs to settle down, and that's why we need this termination on this side to avoid the bounce back and forth of the reflected signal. So that's why we still have to terminate it, right? And then at that point, there is no differential voltage. We would have the common mode of the receiver's common mode like the way we have it, right? So when we encode things in this way compared to the regular voltage mode driver, where is the improvement or the benefit comes from, right? So this is best understood if I put the output signals on top of each other. So this on the left side is the regular energy voltage mode, and if you want to look at the right side is showing the transition encoded voltage mode, right? So these blue lines are showing you the energy encoded voltage mode driver, and the red one is the transition encoded. And you can readily see the difference, right? So when the data are alternating 1, 0, 0, 1, that means it pretty much work like a regular voltage mode because this switch is never come into the action. And without this switch, we are basically my regular voltage mode. Maybe the bits are not directly connected to the switch, but output looks identical, right? But as soon as I start getting a whole bunch of 1s, then the signal goes back to the differential common mode, which would be 0 in this case, right? And the same happens when you get a whole bunch of 0s, then rather than staying here, it goes to the middle of it. So basically, anytime you have consecutive 1s and 0s, the signal will go back to the middle of it. So the benefit of doing this means that we can look at the transmitter current now, right? So in a transmitter current, regular voltage mode would always consume the same amount of current, right? And that's why it's a flat line. It means that whether I receive 0 or 1, I simply change the polarity to which I throw the current through the resistor size termination, its direction differs, but the current that I draw from the transmitter remains constant and it doesn't change, right? And that's where there is an opportunity of power saving, because transition encoding, what it does is that if I see consecutive ones, then I pretty much shut off drawing any current. So what I do is that I basically say all these switches are off, means there is no current path here. And I'm basically telling the receiver that I'm sending you to common mode 0, and what you need to do is to keep the previous data as is, means there is no change. And those are the times when my current goes to 0, right? And that's where I hope to improve efficiency, right? So one simple way to show this is to show the transition density versus normalized signal power, right? And what it shows is that when you have 100% density, you are basically going to be same as the regular. Possible to somehow take this, get this video of the screen. Okay. So now what it shows is that at 100% speed, you are just same as the voltage mode, but as your transition density starts to drop, you will have more of these flat parts where you are not transmitting any current, and your signaling power that you burn would start to reduce. Now we know that random data has 50% transition density, so the best I can do is 2x. If we don't do anything else, is the 2x would be the limit. So it improves, but not order of magnitude, and it's hard to get order of magnitude. And that is where we think that this part that we cannot explore without doing anything to the data, pre-coding or pre-processing might help. It might help us to push this limit, because then we have some sort of way of controlling the transition density to push this signaling power limit to even further, right? And that's what we will be talking about in the next section. But before going there, I wanted to clarify what the receiver needs to do in this case, right? So the receiver for a regular transmitter is fairly simple, and we know these eye diagrams, what they represent. The top one is 1, and the bottom value is 0. So making a decision means just setting a threshold in between on the receiver side, and that will tell me whether the transmitted bit is 1 or 0. On transition encoded case, it's not so simple, right? Because now I have 3 levels. This is 1 level. And then when I am basically sending the common mode or not sending anything, and this is the bottom level, right? So this guy is basically 1, and this guy would be 0, or more like this is 1, the last bit being 0, and this guy is 0 being the last bit 1. And when there is no change, it goes to the middle, right? So to build the receiver, the way we do it, there is more than one way to do it. This probably is a simpler one to think of, is that after we taking the signal, I actually need to set 2 thresholds, one at plus alpha and one at minus alpha. And then once these 2 comparator outputs are available, then I have to convert it into digital values, right? And we know that thermometric to binary, it converts it in this way. So 3 comparator output maps to 2-bit. And if you have, say, 8 comparator outputs, maps to 3-bit, and in this sort of way. So the 2 comparator output would effectively, information-wise, would be 1.5 bit, right? So obviously, we don't have a fraction of a bit, so we still use 2 bits to represent 1.5 bit information, right? So what it tells you whether it is 1 or 0 means if it is above this guy, then the current symbol is 1, and if it is below this, then the current symbol would be 0. And when it is in between, that is the no change. And no change basically says retain the previous information. So you can think of it's a delay comes back and with a marks. So the receiver needs few more extra logic gates, but it's not a whole lot of logic gates. So the complexity wise, when we look at it, it's still really low power solution, and the power savings from the transition density still holds true. So we actually collected a whole bunch of such channels and tried this signaling and see how fast we can go. So obviously when we are trying to do it at 10 gigabit per second, these channels are so good that I don't even need any equalization. This 3 dB is the minimum equalization that I could push, but even if I set it to 0, the eye looks pretty decent. Now, when we go to the 20 gigabit, then there is about 10-15 dB loss there. So that needed about 6 dB linear equalization and still have a fairly decent eye opening for those. So we have done many of these channel analysis, and I don't want to go through all the results, but this is kind of just the summary of it, that you can do it very efficiently. So now the other part that comes into, like one of the papers that IBM published recently, they're looking for this type of links to in a broadcast mode, meaning a transmitter needs to send the data and there would be multiple drops. So in this case, they were talking about 8 drop. Right? So these type of links, what they need is an AC coupling. It's a small AC coupling capacitor so that the loading would not be too significant, right? So nice thing about it is that in this type of signaling, right, some sort of AC coupling comes natural, right? Otherwise, energy signal needs to be very careful how it provides the AC coupling, because a significant part of information is at DC. So what people used to do before was alternate mark inversion type encoding, or even 8-bit, 10-bit type encoding to reduce the content at DC. And this spectral energy versus frequency actually captures that DC content I'm talking about. If you look at energy, it has significant energy at 0 frequency, means at DC. But when it comes to some sort of coding, it is able to reduce the content at DC, because any AC coupled interface will not be able to support the DC. So, but when we do this AMI or any other sort of encoding, a common thing that always happens, I push this spectrum out, but I create a high frequency content that the receiver needs to support. And that creates other energy efficiency issues, because if I have to support wider bandwidth, I have to burn more power. There isn't any easier way out of it, right? What is interesting about it, when we do this transition encoding, this sort of AC coupling comes sort of for free, right? Because what I'm showing is that the spectrum of these regular energy signal, and that obviously have large DC content, but once they're transition encoded, it shapes like this, but there is no spillover to the higher frequency. So the circuit power wise, I can still stay in the same way, right? But one thing has to be understood is that this does not come for free, right? If you look at the height of this eye, and here it's broken into two eyes, so I pay some SNR penalty because of this. It's not exactly 6 dB, it is less than that, because my noise integration window is also a little reduced, and there are a few other differences. Some people say it may be as low as 3 dB, but it's somewhere between 3 to 6 dB, the SNR penalty that I pay for having this free AC coupling interface. So now going to the next part of it, what it is that if I have to reduce the transitions to make this link really efficient, I have to do some sort of data processing ahead of it. Now we can, and the transition encoder is from data to transition convert is very simple. It's just a couple of logic gates. It's as simple as that. So that one is not the issue, but this data pre-processing computation is something that concerns us, because anything that we do here is going to burn power, and overall how much power I will be saving would be offset by this extra computation. So the simplest would be if we could just take some of the computation that naturally happens in machine learning and use that, right? Rather than doing extra processing and reversing it back on the other end. It's best to use some of it that's already there. And this is where I'm not the expert in it, and I do not know how these convolutional neural networks work. But what we saw in most cases, it seems like this DCT is cosine transform is done. Is somewhat at the input of it or somewhere along the process. So I took two examples of showing where they are done, and this example shows that if they do the DCT ahead of it, that sort of gives them some benefit in terms of converging the computation of the actual CNN gets simpler. So what we thought of, without spending much time on it, because you guys probably know this better than I do, so we simply thought of doing the DCT ahead of it. And how it helps us is that once we take sort of any image as an example, and DCT sort of creates this matrix, and once it's quantized, in a lot of the places, the data are static in a way, they are all zeros, right? So the number of elements that are zeroed out here, that has some impact on the image, but assuming that it holds most of the information intact, we would probably still be able to recreate and get the job done what CNN needs to do. But that's a bit of a if. We need to verify that, and probably some of you can tell us more about what is the best way to make that assumption, right? But to us, that's a good start point. And we try to sort of look at it qualitatively. And what it means in an 8x8 block, starting from all 64 elements, if I zero out a few of them, how much the image quality degrades. And obviously, if we throw out many of them, then it's a very blurry image. That probably is never acceptable. But somewhere in between, we can still keep the information intact and still be able to throw out a lot of elements, right? So what we did there is, from that point, we looked at the transition density of those data values, right? And this sort of changes linearly, right? So this blue line is the transition density, and this red line was the image quality. So if you say that I'm going to keep the complexity or say the quality within 10% degradation, then this would be the point, right? I still have to retain, say, about 36 elements in that 8x8 matrix. And that itself would reduce the transition down to only 12%, right? And when I map it back to the signaling power, that allows me to go to somewhere close to 12%, but obviously there would be some overhead. But nevertheless, I'm not just at 50%. Now I am dropped here, where compared to the other signaling, I would be saving about 8x improvement. So that's where we think that doing it together, there is a synergy in it. So 1 + 1 is more than 2. Like, I'm doing some information truncation on this side, but my signaling is able to utilize it and give me 8x improvement. And that's very hard to achieve on any signaling so far, right? So that's what we have been working on, right? So now when we have to look at the DCT complexity and power, and that's where the mixed signal computation comes, because the ones that we find, it's already sort of well documented how much power, how many logic gates should be. For example, in one of the examples that published in 65 nanometer, if you want to run it with a high throughput, like 800 megahertz or so, it consumes about 135 milliwatt, which is significant, right? So if this penalty, if we could reduce somewhat lower, that would be good. Now also, because some of these interface would be on the memory side, and the DRAM logic process is not as good as your regular logic process. So doing the computation on that side, the power can be even higher, right? And that's why we were sort of thinking of, let's do the time domain arithmetic to it. So I'm running out of time, so I will not go into the detail of it, but I'll say the important aspect of it. What it does is really that it actually, if you think of the VCOs are natural phase accumulators, right? And this accumulation process, if controlled properly, it can reflect the accumulation we do digitally to represents multipliers, adders, etc. Right? And what we need along with it is the digital to time and time to digital, because it's just only this part that can be done in time domain. We eventually have to interface to a digital world, right? And if we take a 4-bit multiplier example, right, its area is comparable, but the benefit comes in the power. And when do a fair comparison, we have to look at it time to digital converter and digital to time converter. And if those two blocks were not there, probably you would see a much more power benefit, but those are integral part of it, and this is the real penalty that we have to pay. So this is just the layout of the block. And when we looked at the performance of it, it's actually the interesting part is that for high resolution, it's very hard to preserve the resolution in time domain, at least when it is converted to digital. The time TDC resolution would not be there. It's very hard to support. But if you're in moderate resolution and high speed, then there is significant power benefit to be gained, right? And that's what we are hoping to achieve. Of course, the gate count at some point actually goes up fairly high because of those conversion process, right? There is more information on this on one of the work that we published in TVLSI, but we want to leverage some of this approach when we would be doing in the DCT. So the way it would look like is kind of like this. So we break this thing into two parts. So this part will really be time domain computation and encoding. That's what it says, analog mixed signal computation. And this part is just the link design. But hopefully it's more information efficient than the others. So I have one student that already started January this year, but she's going through coursework and all of that while doing it. So the progress has been there, but as we all know, the training process is there and that takes time. I had an undergraduate student who worked on it last year and also working with me this year. So that's the encoding part of it. And this link design, because of all the things it needs, I have a PhD and a master's who are working together on this. So that's kind of my resources are distributed. So in terms of timeline, where we are looking at it is that we have finished the behavioral, we have collected all the channels, we have done the simulation, shows what is doable there. Right now we are in the implementation phase, right? And then we have to do we want to take this thing to hardware, right? Because that's kind of, we are the lowest level, closest to the hardware. So we want to be able to come up with hardwares that we can demo. So, but that tape out is probably end of the year. And it's not I would not say it's a slow process, because the student just start a year, and within a year be able to tape out would be pretty good, because the coursework takes 2 semesters. So that's why it's not doable faster, and the availability of the timeline. So that's why this fabrication, these two are TBD, depending on when the schedule is offered by CMC. But we hope to be able to done with the things by November this year, in terms of the very close to the physical design. So that's about it for me.
Thank you, Masum. It's a very interesting talk. And maybe we should start afterwards. We have time over the week. If we have questions from the audience, how do they do it? Just they type it, or
they can
just
talk.
speak? Yeah.
Unmute themselves.
Yeah, I have a question. So regarding the transition encoding to minimize power consumption, one thing I am aware of regarding schemes that attempt to use that is that if you have a long run of 1s or 0s, you lose sync. How do you keep synchronization?
Oh, that's a very good question. So it is basically the transition are used for timing recovery. And once you know the edges, so this transition create the edge to explain. Go back to this figure here. So one way to look at it, the transition are going to cause these edges, right? And once we know the edge, then I know where exactly to sample. When I am losing those ones and zeros, then I would, the consecutive ones and zeros, then what is going to happen is that I'm going to lose away those edge information, so I would not know where to sample, right? So the way these links are, most of them are source synchronous, means that I have a clock that comes out of from the transmitter. It's a clock forwarded link. And in these links, what happens, most of the variations happens together. So first of all, there wouldn't be any frequency offset. There would be only time skew, and the time skew can be calibrated once, but over time this skew is going to drift. But we hopefully be able to calibrate most of the fast or relatively fast drifting skew that just calibration would be good enough for us to keep us in sync. That's a good question.
Okay, thanks.
Okay, I guess we have no more questions. Thank you, Masum. This was very, very productive for everybody. And we're looking forward to the next one. We're going to notify everybody whenever we have a new volunteer. And we're looking forward to seeing you all at the AGM on July 5th and 6th. Thanks, everyone.